Welcome to The Explainer. So today we're diving into a genuinely mind-bending reality that's unfolding right now in computer science. Look, we've known for a long time that AI is great at memorizing formulas, right? It can calculate answers at literal lightning speed. But what happens when you ask an AI to discover something entirely new? Well, today we're exploring a system that isn't just regurgitating textbook math. It's actually discovering brand new, mathematically sound solutions.
Which brings us to this massive, really fascinating core mystery. Can an AI actually solve a math problem that no human has ever solved? You know, it's pretty easy to test an AI on a known exam where the answer key is just sitting in a database somewhere. But open mathematical proofs? That is the ultimate test of true reasoning. There's no answer key. The system has to generate a novel, logically flawless path from a known starting point all the way to an undiscovered truth.
The issue we've been running into is that current approaches just fall incredibly short when you push them into this uncharted territory. When you ask existing large language models to conduct novel math research, they tend to just confidently hallucinate. Their logic completely breaks down. They might actually start a proof brilliantly, but then, halfway down the page, they make one tiny fatal error in logic, and they just keep blindly building on top of it. So, if AI is ever going to be a genuine research partner, we absolutely need a new framework.
All right, here's our roadmap for this explainer. 1. Solving open math problems. 2. The ProofCouncil architecture. 3. Step-by-step methodology. 4. Testing on real math. 5. Results and limitations. And 6. Impact on future research.
Okay, Section 1. Solving open math problems. The researchers behind this framework introduced a system they call ProofCouncil. At its most basic level, ProofCouncil is an open-source mathematical AI agent. But instead of just being one single model spitting out an answer to a prompt, it tackles unsolved problems using a highly structured author-critic architecture. It essentially breaks the thinking process down into distinctly different roles.
To really wrap our heads around this, think of ProofCouncil like a mini research department. First, you have the author. Imagine a brilliant but maybe slightly erratic mathematician who is actually drafting the proof. Then you've got the critic. This is a ruthless peer reviewer, and its only job is to find flaws in the author's math. When the author gets stuck, they can turn to the council, which is basically a panel of expert AI colleagues to bounce ideas off of. And finally, there's a compute node. Think of that as an ultra-powerful calculator specifically there for testing the underlying logic.
Moving on to Section 2. The ProofCouncil architecture. When you look at the workflow, it's pretty incredible how the information flows. The author sits at the starting point, generating that initial proof draft. It then sends that draft over to the critic, who evaluates it and fires feedback straight back. So it becomes this continuous iterative loop. And at any point in this cycle, if the author starts struggling, it can optionally tag in the LLM council for some high-level strategic advice or ping the compute node to do some heavy lifting on the calculations. The author takes all that feedback, revises the proof, and the loop just starts all over again.
Section 3. Step-by-step methodology.
So let's break down exactly how this operates. It works in a very strict input, process, output cycle. Step 1 is the input. You hand a complex, entirely unsolved problem statement to the author. Step 2 kicks off the process. The author writes out and compiles a rigorous mathematical document, specifically a LaTeX draft. Step 3, the critic swoops in, evaluates every single line of that draft, and returns a detailed list of errors or logical gaps. Step 4, this loop just repeats over and over. And like we mentioned, the author can ask the council for help if it gets stuck on a really stubborn gap. Finally, Step 5 is the output. But here's the key. The final, verified proof is only returned when the critic finds 0 errors. Period.
But wait, there is a catch here. If a critic works with the same author for too long, they might actually start agreeing with bad logic just because they've been arguing about it for 10 rounds. It's a real issue. Well, ProofCouncil solves this brilliantly with a dual critic system. The stateful critic is the one that remembers the whole conversation history. That helps guide revisions and track progress. But every 3 rounds, a fresh critic is brought in. And this fresh critic, its memory is completely wiped. It provides a totally independent, unbiased audit. It entirely prevents the AI from getting tunnel vision and accepting a flawed idea just because it remembers suggesting it earlier.
All right, Section 4, Testing on Real Math. Now, the crucial number to remember here is 6. In a major competition called the First Proof Challenge, AI teams were tasked with solving 10 open mathematical problems completely autonomously. ProofCouncil successfully solved 6 out of those 10 problems, up to at most minor revisions, totally crushing all the other participating teams in AI systems.
But they actually didn't stop there. The researchers reached out directly to human mathematicians and collected 30 real open research problems that those humans were actively stuck on. Let's focus on the 21 problems where human feedback was fully returned. The results are frankly stunning. ProofCouncil handed back 5 completely correct solutions to problems humans hadn't solved. 2 more are currently considered highly promising, just pending final verification. 8 showed really meaningful partial progress. And maybe most importantly, even when it failed safely. Not a single human expert reported that an output claiming to solve the problem was mathematically incorrect. Though to be fair, in 2 cases the AI did misunderstand the prompt and ended up solving an easier version of the problem.
To really put this into perspective, let's look at a specific case study. Erdish problem 539. This is a real, stubbornly open problem in number theory. The goal was to find the minimum possible size of a specific cofactor set. For years, the traditional human approach had bounded the growth at n to the power of 2/3. Well, ProofCouncil was fed this exact problem, and it used an entirely novel, out-of-the-box approach, a separated suspension construction from a base strip. The outcome? It proved a tighter sub-exponential bound, hitting a dimension-free power exponent of 1/2. It quite literally pushed human mathematical knowledge forward. It's generating mathematically sound progress, not just spitting back what it read in a textbook.
Section 5. Results and limitations. Okay, but let's talk about the heavy lifting. Where is all this computing power actually going in that loop? Well, nearly 50% of the computing power and the cost goes strictly to the author generating those initial proofs. Another 32% goes directly to the critic for reviewing them. This constant back-and-forth generation and intense verification takes immense processing power.
And that immense processing power translates directly to this number, $213. That is the average cost to attempt a single open problem. Look, compared to your standard AI query that costs fractions of a cent, $213 per attempt is a massive leap. Now, sure, it's definitely cheaper than paying a human researcher for months of work, but in the pure context of computer science, scalability at that price point is a very real issue right now.
And beyond the high cost, there are definitely some functional limitations we need to be honest about. First, we have what they call local minimums. The AI will sometimes get stuck in a rut, repeatedly trying to patch one tiny logical error over and over without stepping back and realizing, hey, this whole approach is actually flawed. Second is misinterpretation. Like we saw earlier, if the human prompt isn't perfectly worded, the AI might accidentally solve an easier, unintended version of the problem and confidently declare victory. And finally, human readability. While the math itself is brilliant, the AI lacks that human intuition for pacing. It produces these incredibly mathematically dense, unpolished proofs that take human experts surprisingly long time to unpack and format for an actual research paper.
And finally, Section 6, Impact on Future Research.
Now, what's incredibly cool is that the developers didn't just build this powerful system and lock it away in a vault. They open-sourced the whole thing. They built this visual node editor where researchers can literally drag and drop different AI agents to build their own custom workflows. So if you're a researcher in chemistry, physics, or even economics, you can use this interface to visually build your own custom AI research team. You can set up your own distinct authors, critics, and councils perfectly tailored to your field.
So let's wrap up our whiteboard lesson with the key takeaways. The core problem is very clear. Standard language models hallucinate and really struggle to reason through novel, multi-step open math problems. The solution we looked at today is ProofCouncil. It's an iterative author-critic loop that brilliantly uses both stateful memory and fresh memory wipes to rigorously audit its own logic. The results? Undeniable. It achieved state-of-the-art success on real, unsolved research problems. And the broader impact is huge. It definitively proves that right now, even with those high compute costs, AI can autonomously push the boundaries of human knowledge.
Which leaves us with one really fascinating thought to close out this explainer. If an artificial intelligence can autonomously solve an open, previously unsolved mathematical problem today, what foundational mystery of our universe is it going to unravel tomorrow? Thank you so much for watching, and keep questioning.